Hi, and welcome to this video on the Fundamental Theorem of Calculus. This is actually a two-part theorem. We're just talking about one part of it this section, and that will be the definite integral portion. And what they're saying here is that if you anti-differentiate the function with respect to x, that's going to tell us who we're allowed to do the power rule on, who our base is, etc. That's why this f turns into capital, because this is the antiderivative of the function evaluated at b, your upper bound, minus your antiderivative of your function, so again, capital F, evaluated at your lower bound, a. So there are many visuals, animations, demonstrations, all of that in your book or in videos. I'm going to focus on the actual algebra computation of all this so that we can see how this looks. Now, it is important to note that our function that we're anti-differentiating does have to be a continuous function throughout that interval from a to b. Otherwise, we can't integrate it. So let's look at how we do this. And again, we have so far basic power rule under our belt, and that's about it. So a lot of these are going to have a rewrite. But if I rewrite this, I'm kind of in same boat of trouble here as if I just leave it alone. So here's my rewrite. Now I'm going to say real quick here, and I'm going to try not to say this too often because I don't want to be too repetitive in this video, but this is my function which represents the height of my rectangles at any given x value. So for all those subintervals or rectangles that we're going to put in, we're obviously putting in an infinite amount. That's what the Riemann sum allowed us to do to get to that definite integral right there. And this dx portion is the width. So if I leave off the dx, I'm actually only calculating the height of that rectangle and not the width of those rectangles. So that's not appropriate. Also, I don't know what variable I'm anti-differentiating with respect to because I don't know who I differentiated with respect to. So that variable there, dx, is very important. That's going to match the variables that you see in your function, as well as that's telling you what the bounds are in terms of variables. So it's a very, very important thing to write down, and I think a lot of people when they're starting integration don't write down the dx, and it's very, very important. So it's also important to note that not just the 3 over x has the dx, the whole function, right, is the height, and so that goes in parentheses. All right, now if I think power rule, I could do the power rule on x to the first. We know basic anti-differentiation was we added 1 to that exponent, so that'll become x to the second, and we divide by that new exponent. And that's fine for the first term. But then if I integrate the second term doing the same thing, I'm going to keep my coefficient of 3, but when I add 1 to negative 1, I get 0, and then divide by that same number, that gives me trouble. So this rewrite actually does not help me, which means if I look at this 3 over x here, minus 3 over x, I should know how to anti-differentiate that. So we need to think about whose derivative would give me 3 over x or 1 over x or a constant over x. And that was our natural log. Remember, that was the du over u, or the derivative over itself. So this is going to be minus 3 natural log of absolute value of x. And we'll just talk real quick 1 minute about why it needs to be absolute value of x. Right here in my original function, the only restriction for x is that x cannot be 0. So I need that restriction to match in my antiderivative as well. So I still cannot take the natural log of 0, same restriction. But natural log, I cannot take the natural log of negative numbers. And we talked about that a while back, and that's because anytime you raise e to any power, positive or negative, you will get a positive output. So in order to keep these domains matching, I want to be able to put in negative values for x sometimes. Not in this case. I recognize I'm only going from 1 to 4, but I need to be careful. So just anytime I'm anti-differentiating 1 over x, I'm going to say it's natural log of absolute value of x. And we're going to evaluate this. So some people put a bracket or some just a straight line from x equals 1 to x equals 4. So what the fundamental theorem of calculus tells me is that I'm able to substitute in my 4, subtract, substitute in my 1, and I will get a value for the actual area under this curve from 1 to 4. So I'll put in the 4 first. Everywhere you see an x, you're going to put a 4. I don't need to say absolute value of 4 because 4 is already positive. And then I'll substitute in a 1. Again, 1 is already positive, so I don't need those additional absolute value bars. So 4 squared, so that's 16 over 2 is 8. And now I'm just doing some computation. Minus 1/2. Just be careful that you do distribute this negative sign. Now, I say that, but then 3 natural log of 1 is 0 because natural log of 1 is 0. So I really wouldn't have gotten caught. 8 minus 1/2, so that would be 7.5 or 15/2 minus 3 natural log of 4. There are certainly other ways you can write that. They almost always want that answer to be exact, so that's where you would go ahead and stop. And then I can actually check this on my calculator, so I will show you. You do have a function integrate, so not necessarily checking this graphically, because again, I'm not doing this section right here with a graphical approach. This is more of your algebraic or numeric approach. So if you go under your math menu, choice 9 is function integrate, and that's what we want to do. If you have the new software, this is what it's going to look like, and I'll show you in a second what the classic software will look like. So I literally type in my problem from the very beginning, from 1 to 4. I want to integrate the function x minus 3 over x, and with respect to x. Just checking I typed everything in right, and it's going to give me the decimal. And this is where you're going to have to rely on your computation, right, to get you this exact value, and then you just check it. So is my value matching what they're saying that decimal should be? And again, I'll just close my parentheses here. I'll make sure I typed it in correctly real quick. Yep. And those two decimals match, so I know that I've come up with the correct antidifferentiation of this function. So I know the exact area under the curve from 1 to 4 is 15/2 minus 3 natural log of 4. And again, 3 natural log of 4 could be written as natural log of 4 cubed or natural log of 64 if you like that better. Doesn't necessarily mean you're going to be able to combine your like terms because they're not like, but I can't add those. Okay, so let's look at something different here. Let's look at this problem. And I am going to tell you that when at all possible, and this will carry you through your Calc 2 class as well, I'm going to take that coefficient, because that's a constant coefficient of my whole problem, and I'm going to move it out front. Because again, I know that coefficients are going to stay. They're not going to change. They're not going to go away. So I'm going to just pull that out front so it's sort of not in my way. I also do see a product, but see, we're not operating under a product rule or anything like that. So I'm definitely going to have to multiply this out. So I have 4, the antiderivative from 0 to 3, and then I'll multiply this. So I get 2x squared. This would be plus 3x minus 2x, so plus 1x minus 3. And this is something that I can anti-differentiate. So it just took me one sort of rewrite step, if you will. Again, when you were doing derivatives, you were probably told to try to be as efficient as you can when you're doing those. I certainly could have used product rule if I was trying to find the derivative, but we probably said, let's look for a more efficient way. And that was just leading you into integration where there isn't right now this product rule, so to speak. So I don't have that option. Okay, so now I'm going to anti-differentiate this. So again, keeping this 4 here outside the whole problem. This 2 will stay along as a coefficient. Keep your base the same. I will add 1 to my exponent and divide by that number. Coefficient stays, add 1 to my exponent and divide by that number. And remember, this is really minus 3x to the 0. And so when I add 1 to that exponent, I do get minus 3x to the first over 1, and I'm evaluating this from 0 to 3. So I can put in, I'm going to keep my 4 out in front of everything, and I like to start these from the beginning. Sometimes I have to squeeze things in there, but I should be able to fit that in that space. So I'm going to evaluate, for example, my antiderivative at 3 minus that antiderivative at 0. So if I put a 3 in, I have 2 times 27 over 3 plus 3 squared is 9 over 2 minus 3 times 3 is 9. And then if I put 0 in, don't just assume everything is 0, because things like cosine of 0 is not 0, e to the 0 is not 0, and so forth. So really substitute in 0. I do get 0 plus 0 minus 0 in this example. And then I have a 4 still on the outside of everything. 27 divided by 3 is 9. So 18 minus 9 is 9 plus 9 halves, or 4 times, that would be 18 halves, so 27 halves. So 54, I believe. And again, this is something I would absolutely check. I'll show you using the old software on this one, or the classic software. So I'm going to change to classic. If you have that math print or that newer software, go ahead and stay there. So now when I hit Math 9, this is what it looks like. I'm going to type in the function that I want to integrate from the very beginning. I'm not going to rewrite or change it at all, just in case I had an error in my rewrite. Okay, so this is what I'm going to type, 2x plus 3. All right, let me just make sure I typed my function correct here. 4 times the quantity x minus 1 times 2x plus 3. Okay. Now what you're going to do is put a comma, which is right above your 7, and you're going to say, with respect to x, so comma x, comma, from, now your bounds, 0, comma, 3, and you can close your parentheses. So you're integrating this function, comma, for all x, that's like our dx, comma, from 0, comma, 3. Hit enter, I get 54. Again, if you're on that math print and you hit Math 9, it looks just like it does on your paper. So when I hit Math 9, I go 0 to 3, and I type in my function, and it should give me the exact same answer here, and it looks the same as well. So a lot of people, if you have the choice, they prefer certainly the math print. Just, you don't have to type as much. Or really it just looks the same. Same answer. Okay? All right, so let's look at an absolute value problem, and I'm going to give you 2 options that you have. You don't always have 2 options. This one is just a little bit special. But before we do that, I want to make sure you know about an absolute value graph. And most people recognize absolute value graph to look something like so. These are supposed to be lines and be straight. And so what an absolute value graph actually is, it's actually a piecewise. because this is a line in the first quadrant, right? That's like a y equals x line, and that's for all x greater than or equal to 0. But then on the left side, that is a negative sloping line. That's the line negative x when x is less than 0. Or, oh, well, I'll just say that. Okay? And so really, absolute value is a piecewise, and so we have to use that definition of that piecewise to help us figure out where that vertex went and if that's in sort of the center of my area. So let's look here. If I want to find the antiderivative or the area under my curve absolute value of x minus 1 from 0 to 2, here's my visual of this, okay? My absolute value of x minus 1 is going to shift my graph over 1 to the right. So you'll notice my vertex is now at 1, 0. And so my lines aren't just y equals x and y equals negative x anymore. I actually wrote what the definition of absolute value will help you with. If what's in your absolute value turns out positive, well, that would turn out positive if x is greater than or equal to 1 or on the right side of that line. Then I'm just on that positive sloping line, x minus 1. But if inside of that is negative, okay, then I need to take the opposite of that because absolute value needs a positive output. So even if you're saying, for example, absolute value of negative 3, I know that to be 3. So if what's inside of the absolute value turns out to be negative, I want something to tell me to take the opposite of it. And so that's that negative in the second part of that definition, just like we did above, only this one is shifted 1 to the right. So it's not exchanging functions at 0, it's exchanging functions at x equals 1. And what you'll notice on this problem is conveniently my vertex is halfway between my bounds. So I'm integrating from 0 to 2, and my vertex is at x equals 1. That is not always the case, so we don't always have two options. So option A is you adding these two areas together, and you can see I went through that for you. So the left area is from x equals 0 to x equals 1, and you're on that negative sloping line. And then the sorry about that. The right-hand side, or from 1 to 2, is the positive line, right? And that's that right-hand side underneath here. Okay? So I can add these two areas together, and I get an area of 1. All right, the other option is only an option when the vertex is in the exact center or middle of your interval. Then you can find one of those areas and double it. And you can see that in both cases, I am getting 1 as an answer. So let's just look real quick at y geometrically. So geometrically here, if I look, I can see, yes, these are both triangles, but I can see that the area from 0 to 1 on the left side, right in there, is going to be the same as the area from x equals 1 to x equals 2. And so I can find one of those areas, either one I want, and double it. But again, if I was integrating from 0 to 3, this is no longer an option, and I have to go with option A, where I add the two areas together. Sometimes I don't always have both options available. So I hope that helps with one of the absolute value problems. Now let's go back to some of the other algebra problems that we have. So let's say I want to integrate this function, x squared minus square root of x all over cube root of x with respect to x from x equals 1 to x equals 64. again, I see sort of a quotient here, and some of you might have, if I gave you this problem and said find the derivative of this function, some of you might have used quotient rule, and we probably would have said that it's not necessarily the most efficient, although it worked. There is no quotient rule for antidifferentiation, so in that case, you have to go through a rewrite. And so we were trying to prep you early on efficiencies, trying to get you used to how do you rewrite this. Now, you can take this x to the 1/3 that's in your denominator, and you can write it up here in the numerator if that helps you. Okay, but again, you're going to have to distribute. You can also just separate and reduce, so you can say x squared over x to the 1/3, and then subtract those exponents from there, and then minus x to the half over x to the third, and subtract those exponents from there. It doesn't matter to me whether you view it as a negative exponent and then multiply it in, or whether you separate into two separate fractions and subtract your exponents from there. You get the same thing either way. So I'll have 6/3 minus 1/3 is 5/3 minus, keep your base the same, 1/2 minus 1/3, you're turning those into 6. 3/6 minus 2/6 is 1/6. Again, with respect to x being so important here. So now I don't think this is a big deal other than maybe some of that computation, but we'll see here. So I do add 1 to my exponents. If I add 1, I'm adding 3/3. That becomes 8/3. So I divide by 8/3, which is the same thing as multiplying by 3/8. Minus, I'm going to leave myself a little bit of space here because I know there's going to be a fraction involved. My base is x. I'm going to add 1 to my exponent, so 1/6 plus 6/6 would be 7/6, and instead of dividing by 7/6, we're going to multiply by that reciprocal 6/7, and I'm going to evaluate this from x equals 1 to x equals 64. All right, and then we're going to put in our 64. So I will put some parentheses here and subtract, put in our x equals 1. So I have 3/8 times 64 to the 8/3 minus 6/7 64 to the 7/6. And then I'm going to have my 1, 3/8 times 1 to the 8/3 minus 6/7, 1 to the 7/6. Now, the reason that you can do some of these nicely, maybe even in your head, is because when it's to the 8/3, I don't raise it to the 8th in my head first. Remember, this is your power over root. So I can take the cube root of 64 to be 4 and then raise that to the 8th. Same thing with, I know the 6th root of 64 is 2. And so that's how I'm coming up with these numbers a little bit easier. So the 3rd root of 64 is 4, so I just wrote 4 to the 8th. And the 6th root of 64 is 2, so I just wrote a 2 to the 7th. And then obviously 1 to the 8/3 is 1, and 1 to the 7/6 is 1. And I had quite a bit of computation to do, and I came out with an exact fraction of 1,370,139 all over 56. Certainly I let my calculator help me with that one. All right, so let's talk trig. It's been a little bit. So now we have to know our trig derivatives. So this should not be a new memorization. This should be something that we know from before. So you're asking yourself, whose derivative gets you secant squared t as an answer? So you should be saying to yourself right now, ooh, I know, if I take the derivative of tangent t, I get secant squared t, and you're correct. So literally, the antiderivative of secant squared t is tangent t. And I'm evaluating that from 0 to pi over 4. And so now I'm going to put in a pi over 4, that's my upper bound, minus, substitute t equals 0 in for your lower bound. Tangent of pi over 4 we should be familiar with. So tangent of pi over 4 is 1. Tangent of 0 is 0. So this antiderivative is 1. And I actually think this one is easier to do by hand than it is on your calculator because of two things. Number one, you do not have a secant button on your calculator, so you're going to have to type in 1 over cosine x, because you can change that to x and be fine. And then you're going to have to square it, and you're going to have to make sure that you're squaring all of the cosine x, not just that x of that angle. All right. So the problem becomes when we see trig and we get to a trig function like tangent squared x, and we're like, oh, okay, I should know a derivative who gets me tangent squared x as an answer. Remember, this is kind of like playing Jeopardy. You're just going backwards. Well, we knew the previous one because if I take the derivative of tangent t, I get secant squared t. But unfortunately, there is no derivative that I can take that actually gives me tangent squared x as an answer. But good thing for me, I know a relationship between secant squared and tangent squared. Good old Pythagoreans. So if I can integrate secant squared, which we just did, we just said we could, that antiderivative is tangent x. Then I also can integrate tangent squared x because I can go through a rewrite here like I was talking about, and I can say I'm integrating from 0 to pi over 4, but instead of it being tangent squared x, I think my battery is going, I'm sorry. Instead of it being tangent squared x, I'm just going to rewrite this Pythagorean identity and solve for tangent squared x. So subtract 1 from both sides. So tangent squared x equals secant squared x minus 1. And I'm antidifferentiating this with respect to x. Now I can integrate it. Because the antiderivative of secant squared x, we just said, is tangent x. And the antiderivative of 1, see, if we didn't have this dx here, we wouldn't necessarily know what variable that came from. This came from an x, right? This is really x to the 0. So if I add 1 to that exponent, I get x to the first, divide by 1. And I'm going to evaluate this from 0 to pi over 4. So we need to use our Pythagoreans in conjunction with the derivatives that we know. So then I can replace my pi over 4 in for x minus, put your 0 in for x. So this will be tangent of pi over 4 minus pi over 4. And I'll put 0 in. Tangent of 0 minus 0. So tangent of pi over 4 we said before was 1, minus pi over 4 is just pi over 4. And tangent of 0 is 0, and 0 is 0. So I don't have to say any of those. So my answer is just 1 minus pi over 4. I do have a tangent button on my calculator, but I do have to be careful in squaring that. But you certainly can check this and get the decimal and make sure that your decimals do match. Okay? Okay, so here we are. Speaking of trig, let's try to figure this one out. So I'm integrating from 1 over square root of 3 to square root of 3. I'm not saying this is always going to be a giveaway, but if that's not a giveaway that this has something to do with trig, right, that's a giveaway to me. Now, I did go through a quick rewrite here that this is a coefficient of 8. So maybe, just maybe, you will recognize this as someone's answer when you were finding derivatives. So the better you were at finding derivatives, the better you will obviously be at finding their antiderivatives, because you're like playing Jeopardy. Whose derivative gave you that answer of 1 over 1 plus x squared? And again, this trig should sort of give it away. And because those are side ratios, you're probably talking about inverse trig. And oh yeah, that is inverse tangent of x. So I have 8, right, because we took that 8 out front. That's a constant coefficient. So 8 times inverse tangent of x. Here I'm evaluating that. So I'll put that in. Inverse tangent of square root of 3 minus inverse tangent of 1 over square root of 3. So my upper bound minus evaluated at your lower bound. I drew those two triangles out for your reference. They should be exact, right? So the pi over 3 or 60-degree triangle minus the pi over 6 or 30-degree triangle. Keep those exact. Okay. And you can pause and look at that longer if you need to. All right, so one last thing here. Solve the differential equation. So if I give you f double prime of x, we should be able to find f prime of x. F prime of x would be the first antiderivative, because remember, if we were given f and we take a derivative, we're at f prime, and if we take another derivative, we're at f double prime. So if I start down here at f double prime, in order to get up to f single prime, I need to do the antiderivative one time. So if I antidifferentiate x squared, we did this before when we first started talking about power rule. This will be x to the third over 3, but plus c. And we were given specific information about how to find c in this case, because what I'm told is f prime of 0 is 6. So when x is 0, right, 0 cubed over 3 is 0, my first derivative is 6. So c is 6. So I'm actually working now with a first derivative that is x cubed over 3 plus 6. And this is sort of a review because you did do some of these problems early on when you just first learned power rule. Well, I'm solving the differential equation, so I'm trying to find an equation for the function. So I'm going to do that antiderivative one more time to get to f of x. So if I antidifferentiate that red f prime, I'm going to now be at x to the fourth over 3 times 4, which is 12, plus 6x, plus, I'm going to call it d, so you can differentiate between the c from before and my d now. Again, I'm given information of how to find that specific d. This is not a general antiderivative, this is specific. So f of x is 3 when x is 0. Those are the nicest values we can give. So d is 3. So my overall function that I was supposed to write here is x to the fourth over 12 plus 6x plus 3. And you can certainly find the second derivative, and it should lead you to x squared, which is what you started with. So I hope you found this helpful to get you started with doing some of these definite integrals, and thanks for watching.